So, let me begin by recalling the weak duality theorem. Remember, the weak duality theorem said that if x is feasible for P and y is feasible for B, then C transpose X is greater than or equal to B transpose Y. That is, the objective function value for the primal problem is greater than or equal to the objective function value for the dual problem. After this, I prove that dual of the dual is the primal. So, you might say that okay, so there is no difference, I can treat anyone as the any problem as the primal problem and any other problem as the dual problem. So, then what happens to this inequality? So, that is where a word of caution is necessary, because this is a minimization objective function, this is a maximization objective function. So, no matter what problem you call the primal or the dual, the inequality is between the minimizing objective function and the maximizing objective function. So, this is what you have to remember. So, I thought I will just revisit this and tell you about this, because after this result one might say that there is no difference between which problem you call the primal or which problem you call the dual. So, here we are sort of following a convention that our primal problem will always be the minimization problem and the dual problem will be the corresponding maximization problem. Okay. Now, after this, because for writing the dual to a given LPP, there are many different forms in which an LPP can be written. So, I thought I will just go over the rules again, and of course, it cannot ever be exhaustive. For depending on the situation, you will have to reformulate the problem, but the idea is that you should always reduce your LPP to the standard form and then write the dual. If you can, because it is easiest to remember the rules for writing the dual for a standard form of the LPP. So, let me give you another example to show some more aspects of duality theory, because one can just go on and on talking about dual part of the linear programming problem and the relationship between the two. So, let us take this example. Here I am giving you a tableau for the linear for a primal problem. So, here let us see x1, x2, x3, x4, x5, and this is right hand side, fine. Top row is 0, 2, 0, 3, 2. Objective function value minus of the objective function value is 25. Okay. Then the constraint part is 0, 1, 1 by 4, minus 1 by 2, 1, 0, 1 by 2, 1 by 6, 0, 1 by 3, and the basic feasible solution is 5 by 2, 5 by 2. Okay. And you are told that this represents an optimal tableau for a linear programming problem, and you have to infer a lot of things. So, immediately right now, what can we infer? And of course, so you are told that this is an optimal tableau, this is an optimal tableau. Okay. Then also that x4 and x5 are slack variables. Okay. So, once you know that x4 and x5 are slack variables, that means your constraints are less than or equal to kind. And if the constraints are less than or equal to kind, that let us go by tradition. So, we conclude that the problem is a therefore constraints are this kind, right. And so, the problem is a maximization problem. Okay. Now, if it is a maximization problem, top row, what do you see? Top row, the numbers are non-negative, and if it is an optimal table, and that means this has top row entries are greater than or equal to 0. This implies that the entries in the top row are of the form Zj minus Cj, right? Because if there was Cj minus Zj, then this would be this would not be optimal, right? For a because for a maximization problem, if the entries here were Cj minus Zj, then you can improve the value of the objective function further. Okay, so therefore, if we have assumed that the problem is a maximization problem, then the entries in the top row being non-negative implies that the entries are of the form Zj minus Cj. So, there are some textbooks use this convention, and therefore, I thought you should be familiar with this also. And so, this is all that we have been able to infer from the given tableau. Now, the question that you have to answer is, the first question is, so questions to be answered. Questions to be answered. First, obtain the original problem. So, that means obtain the data. This is the data given to you for the final tableau, and can we get from here, knowing that this is a maximization problem, x4, x5 are slack variables, and yes, and the top entries are Cj, Zj minus Cj. Can I get back the data for the original problem? That means, can I get the Cj's, the matrix A, and the right hand side B, right? Okay, so let us quickly do it. Now, first of all, since x4 and x5 are slack variables, that means when you started the simplex algorithm, these two columns were E1 and E2, right? And therefore, as I told you, because we use the product form of the inverse, that at any iteration, these columns will always give you the current basis inverse, right? So, therefore, basis inverse is your columns right now y4 and y5, the current columns which are here, right, which is equal to half 1 by 6, 0, 1 by 3. Okay. So, this is your B inverse. So, we can quickly compute the B. That means the so what is your basis right now, and this would be half 0, 1 by 6, 1 by 3. So, if the determinant is 1 by 6, so you divide, so that becomes 6. So, 6 times, and if you remember, this becomes 1 by 3, this becomes 1 by 2, this is 0, this is minus 1 by 6, right, which gives you 2, 0, minus 1, 3, and you can quickly verify that this is the inverse, because you multiply by this, you get 1, you multiply this with this, you get 0, then you multiply this with this column, that this gives you 1 by 3, minus 1 by 3, 0, and again this is 1. So, this is the basis. You have the basis, and now from here, because these two entries are zeros, that means this must be the basic variables. But again, the column here is 1, 0. So, therefore, this is the first basic variable, this is the second basic variable, right. So, that means now you have A3. So, this gives you A3, and this is your A1. Is it okay? Because this Zj minus Cj's are 0, so these must be the basic variables, and since the column here, the basic column here is the y3 is 1, 0. So, this must be the first basic variable, and this must be the second basic variable x1. So, therefore, the columns here are A1 and A2. So, now you need to compute A2, right, because A4, A5 you know are E1 and E2. So, I need to compute A2, and A2 is equal to, yeah. So, to compute A2, you know that, okay, let me write it this way, that your y2 is B inverse A2, right. Therefore, A2 is B y2. So whichever way you, so now you have y2 and you have b. So b is, so this is 2 0 minus 1 3, and your y2 is 1 by 4 minus, so this is 1 by 4 minus 1 by 2. Okay. So what do you get from here? This is 1 by 2 and then minus 1 by 4 minus 3 by 2. So minus 1 by 4 minus 3 by 2 is equal to 4 times, this is 4 in the denominator, minus 1 minus 6. So minus 7 by 4, minus 7 by 4. So this is your A2. So now you have the matrix A. You have the matrix A here, and we want to find out B. So again we have that 5 by 2, 5 by 2 is equal to what? This is your B inverse B. So whichever way you, so therefore this implies that your B is B 5 by 2, 5 by 2. So the first question actually is familiarizing you with the simplex tableau and what is where and so on, and then we'll come to the dual part. So this is equal to, again your B is 2 0 minus 1 3, and this is 5 by 2, 5 by 2. So therefore this gives you 5, and then minus 5 plus 8 plus 15. So this is right, minus 5 plus 15, so 10. This is also 5. So you get your B also. That means now that lower part is with you, and finally we want to compute the cost coefficients, right? So the cost coefficients, you have Z1 minus C1 is 0, which implies that C1 is Z1 and Z1 is CB B inverse A1, right? Okay. Now where do I get this? A1 I have already, I have computed A1 here. Have I done that? This is okay. Why have I put this? Okay, sorry. This is A3 and this is A1, because the first basic column is A3 and the second basic column is A1. So this is A3 and this is A1. Okay, fine. So CBB inverse A1. Now remember, because these are slack variables, so and since we are writing Zj minus Cj, so please figure out for yourself. That means, see here what is happening when you look at Z4 minus C4, this is given to you to be 3. Now see, this implies that Z4 is 3, right, because C4 is 0, and this implies, now what is Z4? This is CB B inverse A4, okay, which is CB B inverse E1, right, which is CB B inverse first component. So that is equal to 3. And similarly, from Z5 minus C5 equal to 2, you will conclude that the second component of CBB inverse is 2. So as I have been pointing out even earlier, that the dual solution would be available here. Now we were most of the time talking about the minimization problem, and therefore and since I was keeping Cj minus Zj in the top row, so therefore this was minus CBB inverse, okay. And now, but since here we are keeping Zj minus Cj, so these entries will give you, if you have slack variables here, remember for surplus variables it changes again. So for slack variables, this will give you the dual solution. So the dual solution is 3 2, or your CBB inverse is your dual solution. So once you have this, therefore from here I will get C1 as 3 2 and your A1 is 0 3, so which gives me this value as 6, right. And similarly C3 I can, because I have C3 you can compute, which will be 3 2 for the same reason, no? Because Z1 minus Z3 minus C3 is also 0. So therefore C3 is Z3 and Z3 is C3 2, and the third column is 2 minus 1. So this is 6 minus 2, which is 4. Okay, fine. And let's quickly check that my calculation is okay. Why? How? Because now that I know C1 is 6 and C3 is 4, and the values are 5, 5. So, how much will it be? Okay. So, this will be 6, 5 is 30 and 5 4s is 3 2s is 6 and minus 2 is this thing. So, this becomes 4. So, if my oh, this is my right hand side. Okay. Your solution is 5 by 2 and 5 by 2 currently, the optimal solution. So, therefore, what is the objective function value? Objective function value is equal to 6 times 5 by 2, which is 15, plus 4 times 5 by 2, which is 10, 25. So, my calculations are okay, because this number is here is minus 25, which is negative of the objective function value. Okay. So, we compute, so therefore, this is okay. Now, you need to compute C2, right. Okay. So, let us, we can do it, we can use this part of the blackboard. Okay. So, now Z2 minus C2 is given to you to be 2, right. So, this implies that C2 is equal to Z2 minus 2, and Z2 is CB B inverse A2 minus 2. So, CB B inverse is 3 2, okay, and A2 would be A2 we have computed here somewhere. A2 is 1 by 2 minus 7 by 4, right. So, this is 1 by 2 minus 7 by 4. Okay. So, that gives you 3 by 2 minus 7 by 2, which is 3 minus 7. So, that is minus 4 divided, so minus 2. So, this is the thing, right. A small correction, while computing C2, the minus 2 was left out. So, now please add that also, and then the actual value of the correct value of C2 will be minus 4. So, you can now write the let me write the original problem for you somewhere here. I need this data. So, yeah, this is the thing. So, the original problem is maximize Z equal to C1 quickly. C1 is 6. So, 6 x1 minus 2 x2 plus 4 x3, right, 4 x3, this is the thing, x4 x5 are 0, subject to. So, A1, your matrix A1 is 0 3, A2 we found out is half minus 7 by 4, and A3 is 2 minus 1. So, this times x1, x2, x3, and constraints are less kind. So, this is this, and this is 5 and 5, 5, and x1, x2, x3 is greater than or equal to 0. So, this is the thing, right. Now, you want to say that, okay. So, the second question is write the dual to this problem and find out the optimal solution. So, since you have already found the optimal solution for the primal, then you know that the solution here would be the, because this is a maximization problem and you are writing Zj minus Cj. So, the dual solution is given by 3 comma 2, which is also the optimal solution. You already know from duality theory, right. So, we can now answer the second question. So, the second question is write the dual problem and obtain its optimal solution. Optimal solution, and from our chart we already know that since primal has a finite optimal solution, therefore, the dual is also has a finite optimal solution. So, the dual would be yes, now in this case it will be minimization problem, minimize psi equal to, yes. So, these become so transpose, right. So, this will be, oh well, sorry, first 5 5. So, this will be 5y1 plus 5y2 subject to y2 greater than or equal to the objective function coefficient 6, then the other one is 1 by 2 y1 minus 7 by 4 y2, this is 2, right, which is greater than or equal to minus 4 or minus, what is the coefficient, minus 2, sorry. So, this is minus 2, and then the third column is 2 y1 minus y2 is greater than or equal to 4. y1 y2 greater than or equal to 0. So, I am saying that the optimal solution is y1 y2 equal to 3 2, and just quickly verify that this is feasible. Here sorry, so 3y2, right, 0 3 3y2. So, therefore, 9 is greater than or equal to 6, this is satisfied. Then here this will be 3 by 2 minus minus 7 by 2, which is satisfies as equality, and but you have x1 also in the basis. So, actually, okay, then 2y1 is what, 2y1 is 6 minus 2. So, this is also satisfied as equality. So, what is happening here is that actually this says that x2 and x3 should be okay. If this is this aspect needs to be probably there is some this thing in the, because 3y2 is greater than or equal to 6, this should have been, sorry, all the satisfied as equality. y2 is 2, that is what I was worrying me. So, actually all the, because the complementary slackness condition must satisfy at an optimal solution, right. And so, you see that x1 and x3 are positive in the primal optimal solution. So, these constraints must be satisfied as equality. So, that is okay, and you can quickly check that the value of the objective function is 15 plus 10, which is also equal to 25. So, the calculations are okay, and you see the relationship between. So, therefore, just knowing that this is an optimal tableau for a linear programming problem, you could conclude lot of things, and you could obtain your dual solution, dual optimal solution, and so on. So, the theory is very interesting, and the more time you spend with it, the more you will learn to enjoy it. And this is the idea, that I hope that at the end of the course you really feel that you have picked up some tool that you can really enjoy and use to solve many day-to-day problems. Now, let me go to another aspect of duality, which is very interesting, and that is complementary slackness. Okay. The idea here is that look at the duality theory in a different way, and that is that we say that if x bar is feasible for, or maybe x bar is feasible for P and y bar is feasible for D, and the pair satisfies the conditions, satisfies the conditions x j bar times this would be a j transpose y bar minus, or okay, if I write a j transpose y bar, that will not be correct, because you have x j and this should be your this should be b I. So, I have to have, okay, this would be x j bar, sorry, this is okay, I wrote it correctly, a j transpose minus c j. is 0 for all j, and y bar I minus ai x bar minus bi is equal to 0 for all I. So, this is j varying from 1 to n, and this is. Now, here I have stated these conditions for the canonical case, right. So, maybe I can say that these conditions are for the pair, for the primal and dual pair minimize C transpose X subject to A x greater than or equal to B, x greater than or equal to 0, and the corresponding dual would be maximize B transpose Y subject to A transpose Y less than or equal to C, Y greater than or equal to 0. So, this is known as the canonical pair. You have just inequality constraints of the greater kind. So, one has to keep this in track. If I change the inequalities, then as you saw that your things change there. Okay. So, this is the pair, and for this I am writing. So, it would be a good exercise if you sit down and write the complementary slackness conditions when you have the standard form of the linear programming problem. Okay. Now, okay, have I stated the theorem correctly? If x bar is feasible for P and y bar is feasible for D, and the pair satisfies the condition this and this, then of course, this is just a note, then x bar is optimal for P and y bar is optimal for D. Okay, the converse is also true. So, maybe I should state it as if x bar and y bar feasible for P and D satisfy these conditions, then of course, this is optimal, and the converse is also true. Converse is also true. Now, actually you can try to understand what does that say. See, for example, this says, just look at this. It says that if the dual constraint here, if the dual constraint is satisfied, because the product is 0. So, at least one of the numbers has to be 0, either x bar j has to be 0 or this number has to be 0. So, in case this particular constraint, the dual constraint, jth dual constraint is not satisfied as equality, then this is a negative number, and therefore, x bar j must be 0. And similarly here, if the corresponding primal constraint is satisfied as strict inequality, then it says that the dual variable must be 0. And we will look at the interpretations. I will come back to the economic interpretations of these conditions, but first let us just quickly prove the result. Okay. Let us first do it the first way. They satisfy these conditions. Okay. So, what does it mean? So, I will call this as the first set of conditions, and this is the second set of conditions. Okay. So, sum up the first set of conditions with respect to j, right, and you get what? That summation x j bar a j transpose y bar minus c j is equal to 0, right, and this gives you what? See here, this is x j a j transpose y bar. So, y bar is outside. So, this actually this implies that the summation, if you do it here, I can see this is a single number x j bar times a j transpose, right. If you adding up here x j a j transpose, see when you write this, when you write a x, you can write this as a 1 x 1 plus a 2 x 2, right. I can read this as, how will I read this? This is my matrix, Okay, Ax is A1 to An, and then you have x1 xn, right? This is how you write it. So, you write A1 x1 plus A2 x2 and so on. This is how you can rewrite this. So, same thing I am saying. So, whether I write xj bar aj transpose, or so it will be the same thing as, because it is a single number. By the way, this is, yeah, this is aj bar aj transpose y bar j minus cj. So, therefore, this implies that this is equal to Ax bar, you can say maybe transpose y bar minus C transpose x bar is 0, right. So, therefore, this implies that your C transpose x bar is Ax bar transpose y bar, right, which gives you, and because x bar is feasible. So, therefore, you have Ax bar greater than or equal to b, y is all non-negative. So, therefore, what do you get from here, that Ax bar is, so this is greater, because y bar all components are non-negative, this is greater than or equal to b, my inequalities will be maintained because components of y are non-negative. So, this is greater than or equal to b transpose y bar. Then from here, from the second one, sum up the second set of conditions to obtain conditions with respect to I. Of course, we are summing up with respect to I, and here you will get what? See, this is summation yi bar ai x bar summation over I. I should have said summation over j here, minus is equal to sigma, does not matter what you write, right, yi by I, or this whatever it is, right. Okay. So, then this you can write as, see, yi ai. So, this is a row, and so I can write this as a y bar A transpose y bar times x bar, this is equal to B transpose y bar, yeah, because you are summing over I here. So, the correct equation is actually y bar transpose A x bar is equal to B transpose y bar. I had earlier written it as y bar transpose A transpose into x bar, which would not give you the right. See, on the right hand side the term is 1 by, it is a single number. So, on the left hand side also now it is a single number, because y bar is 1 by m, A is m by n, and x bar is n by 1. So, the product is 1 by 1. So, right now the equation is valid. Now, these two quantities, so here what you have, A transpose y bar, A transpose y bar is less than or equal to C, and again all components of x are non-negative. So, this implies that C transpose x bar is less than or equal to B transpose y bar from here, yeah, because y bar is feasible and all components of x bar are non-negative. Therefore, this is less than or equal to C transpose x bar is less than or equal to this, and so this holds. So, from here this is your 1 and 2. So, 1 and 2 imply that C transpose x bar is B transpose y bar. Okay. And so, what does it follow? And from, therefore, from fundamental theorem of duality, it follows that x bar is optimal for P and y bar is optimal for D. And now you can see the converse also is immediately obvious. I think, see, if so we said that if x bar is feasible for P and y bar is feasible for D, and x bar and y bar satisfy these complementary slackness conditions, then they are optimal. Now, what we want to say is that if they are optimal, x bar is optimal for P and y bar is optimal for D, then you just have to reverse the argument, because in that case, by the fundamental theorem of duality, C transpose x bar would be equal to B transpose y. So, you will have equality, and once you have equality, you see that these conditions will be satisfied, because when you sum up this with respect to j and sum up this with respect to I, the two quantities are equal. So, therefore, the two, and you already know that these two, C transpose x is equal to B transpose y, okay. And so, you can say that each of the conditions will be satisfied, because once you have that this summation is satisfied as equality, right, then since x j bars are all non-negative, so, and these are all less than or equal to 0. So, every term here is of negative sign. So, and sum of quantities of the same sign equal to 0 implies each must be 0, and therefore, individually you can show that this is 0 and this is 0. So, I will leave the converse of the proving the converse. You can now write down the details. I have given you the idea. So, that takes care of the complementary slackness theorem. So, now let me explain the complementary slackness conditions, or try to give you some interpretations to the complementary slackness conditions through the diet problem that we had formulated last time. So, this was the cost of the of a diet, and this was the adequate diet, the conditions for a diet to be adequate. That means, it meets the necessary requirements for the different nutrients. So, this was your problem, and the dual would be of this kind. So, when you say that x j bar times a j transpose y bar minus C j is equal to 0 for all j, and y I bar times a I x bar minus b I should be equal to 0 for all I. So, these are our complementary slackness conditions, and we saw that if the x bar and y bar is a primal dual feasible pair and they satisfy the complementary slackness condition, then they are optimal. So, at optimality, what are we saying? Say, for example, here remember I gave you the interpretation of the dual variables as the value or the prices that a manufacturer attaches to the different nutrients. So, here for example, this gave you the worth or the value of the jth food in terms of the nutrients it contains, right, and Cj is the market price of the food. So, what we are saying is that in case the worth or the value of the jth food in terms of the nutrients is strictly less than the market price, then that corresponding x j bar should be 0 in the optimal solution. That means, the housewife will not include that particular food in her diet if the worth or the value of that food is less than the market price, right, because in some sense you will say that the food is not as good, right. And similarly, from here you will say that, and interpret it this way, this gives you the, you were saying that a I x bar, so x bar is your diet, optimal diet, then this told you the total the diet, the total diet, what is the amount of the ith nutrient it contains. So, this is the total amount of nutrient that your diet contains, and if it is greater than Bi, right, here you have this. So, if it is greater than Bi, then the corresponding Yi bar, because then there is no value to the that nutrient, because your diet already contains that extra nutrient already more than what is required. Therefore, the value of the corresponding dual variable is 0, right. And other way you can say that if you are including a food in your, if you are including the jth food in your diet, then this must be 0, because that means this is positive. So, in that case this constraint must be 0. That means, you will only include a food in your diet provided the value of the food in terms of the nutrients it contains is equal to the market price. So, this is some sort of equilibrium condition, that whatever the optimal solution, the foods that get included in your diet, the corresponding value of the food with respect to its market price is equal, otherwise you do not include it. And there are so many other, we will also talk of some other interpretations, because as we go along we will very often keep visiting these complementary slackness conditions. So, I will come back to them off and on, right. Okay. So, now let us look at this problem, and let me show you another way of we can make use of the complementary slackness conditions. So, suppose you have been stated this problem. This is maximization problem. Conditions are less than, constraints are less kind, variables are non-negative. So, in fact, you can say that this is your dual problem, right. Maximize the objective function subject to less than kind constraints, non-negative variables. So, you want to, so what is you are asked to write the dual of the problem. So, let us quickly write the dual. So, dual of the dual of the given problem will be minimize, right. If you want, you can go through the exercise of converting this to a primal problem, then write the dual, but we have already done it. So, I will just straight away, because this is this form. So, the dual must be this form, since the dual of the dual is the primal, right. So, I will use that concept. So, minimize psi equal to 19 y 1 plus 57 y 2 subject to quickly. So, this is y 1 plus 2 y 2, right, and this is greater than or equal to 10, right. Then the second column is y 1 plus 4 y 2, 4 y 2 is greater than or equal to 24. Okay. Then the third one is 2 y 1 plus 3 y 2, 3 y 2 is greater than or equal to C 3, which is 20. Then the fourth column is 3 y 1 plus 2 y 2. So, 3 y 1 plus 2 y 2 is greater than or equal to 20, and the fifth one is 5 y 1 plus y 2. So, 5 y 1 plus y 2 is greater than or equal to 25, and your y 1 y 2 are both not. So, you can quickly verify that this is a dual feasible solution. 4 plus 10, 4 plus 10 14 greater than 10, then 4 plus what is it 20 24. So, I will mark this because this is satisfied as equality, and I will tell you why. Okay. Then this is 8 plus 15 23. So, this is satisfied. Then 12 plus 10, this is also satisfied. Then 20 plus 5 25. So, this is also satisfied as equality. So, this solution, that is the dual solution given to you, is feasible for the problem, right. Now, let us use complementary slackness conditions. What we said is, if we can find, so I have a dual feasible solution. If I can find a primal feasible solution such that the complementary slackness conditions are satisfied, then I can conclude that, because you are asked to find optimal solutions for both the primal and the dual. So, let me take a gamble. What I will say is, I already have a dual feasible solution. Let me see if I can find a feasible solution for the primal, which together with this dual feasible solution satisfy the complementary slackness conditions. If I can find one feasible solution like this for the primal, then I know that both must be optimal. So, and that is why I mark this, because remember we said that here xj bar can be positive only if the corresponding dual constraint is satisfied as equality. So, I have two such constraints, because this implies that your x 1 is 0, this implies that your x 3 is 0, and this implies that your x 4 is 0. If I have to find x bar which satisfies complementary slackness conditions along with this y dual feasible, then because of this I must have whatever dual constraints are not satisfied as equality, the corresponding xj bar must be 0. So, that means now I have to find a primal feasible solution for which consists of the basic variables x 2 and x 5, right. So, if x 2 and x 5, so therefore, in here you see you make all these zeros. So, what is your which implies, so then when is there, therefore, is there a basic feasible solution for the system, right? What will it be? It is x2, so x2 would be x2, 4x2 and then plus 5x5 and plus x5. So, this is 19 and this is 57, right. If I can find an x2, x5 satisfying these constraints and they are non-negative, then I am done, because I have a basic feasible solution. So, let us quickly multiply this by 4 into 4 and then I subtract. So, what will I get? 20 minus x5, 19. So, this implies that 19 x5 is, this is 4 times and this is 3 times. So, this is 19. So, this implies x5 is 1. So, if x5 is 1, then this becomes 56. So, therefore, 4x2 is equal to 56, which implies that x2 is equal to 14, right. So, that means my I have a feasible solution. So, the basic feasible solution, therefore, the corresponding basic feasible solution is 0, 14, 0, 0 and 1. And they should be optimal. Why? Because the complementary slackness conditions are satisfied. Yes, you may say that I have not checked these, but okay, let us do it. We can verify that these are also satisfied. Actually, this was enough. So, let us see what are the both the dual constraints are satisfied as equal primal constraints, because here you have x2 is 14 and this is 1. So, this is 19, right. Then 4 14s are 56, 56 plus 1 57. So, both the constraints are satisfied as equality, because y1 bar and y2 bar are both positive, right. Y1 bar is 4 and y2 bar is 5. So, you have this, and now we can we have some more checks. We can make sure that the two solutions are optimal. And how do we do that? We will compute the objective function values. So, the primal objective function value is equal to, yes, x2 is 14. So, 14, oh no, that is a big number, 14 into 24, yes, 14 into 24 plus 25. Okay, let us quickly do the arithmetic. 4 4s are 56, 5 4 2s are 28, 28 and 3 33. So, this is 1, 5 and 6, 361, right. And dual objective function is equal to 4 and 5 y1. So, this is 19 times 4 plus 57 times 5. So, let us quickly do it. 76 plus 5 7s are 35, 5 3 5 5s 25 to 8, right. 1 and yeah, 7 8 15 6. So, the two values are equal. So, either way you check, the solution is optimal. So, you see this is also a big tool, because I had feasible solution for the dual. Of course, the question will arise, how did I obtain it? Suppose, and I will show you situations which will very naturally arise, where you might have a dual feasible solution, or it may be very convenient to lay your hands on a dual feasible solution, and then you want to find out whether you can you have a corresponding primal feasible solution, for which together with this dual feasible solution satisfy the complementary slackness conditions, and therefore, you can easily obtain optimal solutions for the two problems. Okay. Now, as I said that the story about the duality theory is not over, because one can go on, and of course, I will show you I will, through using these complementary slackness conditions, in the next few lectures we are going to develop variants of the simplex algorithm. But one more thing I wanted to show you here, and that is, you can another interpretation for the dual variables that we can have is, see, at optimality we have said that your C transpose x bar is B transpose y bar at optimality. Therefore, your Z star, maybe you can say, is actually, you can write this as CB B inverse this times B. Fine. I remember I am reading this always as a row vector. So, if B is your corresponding optimal basis, then this is what you have. Because at optimality, the two objective function values must be the same. So, Z star is my primal objective function, optimal value, and this is, it is equal to this. So, therefore, you can also say that delta Z by delta Bi, if you want to look at the rate of increase of Z star with respect to increase in the value of Bi, then this tells you this is CB B inverse I. So, you see, you have a nice interpretation. Dual variables are, and of course, I should also give you the name which is very common. Dual variables are also called shadow prices. Okay. So, shadow prices is another name, relative prices, shadow prices, and as you read the literature you will find out. Anyway, so this that means the dual variables also tell you the rate of increase of the objective function with respect to the right hand side vector. So, in other words, the yi bar for the diet problem tells you what? So, that is what I am saying, that in case your this constraint is not satisfied as equality, that means the nutrients present in your diet that you have chosen is the ith nutrient present in your diet is less than the required one, greater than the required one, then the worth of that nutrient is not there. That means, if I increase that particular nutrient in my diet, it is not going to help me, because I am already meeting the minimum requirement, and therefore, yi bar is 0. Right. That means, at optimality, if you already have enough of that nutrient, why would you want to increase the content of that particular nutrient, and so yi bar would be 0. That means, the rate of increase, you do not want to increase the content of this particular nutrient in your diet, because you are already meeting the requirement, and many other ways of looking at it of the dual variables. So, as we go on, we will talk about it more and more. And so, next time I will try to, yes, there will be an assignment sheet that I will discuss for consisting of problems based on what we have discussed so far, and then I would like to develop variants of the simplex algorithm using these complementary slackness conditions.